Sairam and welcome to the next session in computational linear algebra. After briefly looking at all the four subspaces and how a matrix is transforming vectors from a space to another, we are going to look at matrices with another perspective called as linear transformations. Let us begin this session with a prayer. Om Sa Ishwaraya Vidmahe Satyadevaya Dhimahi Tanna Sarva Prachodayat. Om Shanti Shanti Shanti. In this session we would like to look at, we have been using matrices. We want to see what is the effect of a matrix on a vector. And if we are able to understand this, maybe looking at the geometry of it or trying to see does a matrix represent some kind of a physical transformation on vectors, we would be able to get more insights on the matrix itself, or we could use the matrix to understand what is the physical action that is being performed on a vector. So we want to get this relation of what a matrix does to a vector. In effect, we can understand that if I have this matrix and take this vector, I get another vector. Okay, similarly I have put down many examples here, right, and we do get the results. But what do they actually mean? Is it getting related to some kind of an action that happens on the vector, right? We will have to look at it. So we want to look at the geometry of it. What we could do is we can plot all this in R2 and see whether really look at what is original x and the transformed x, and then try to see if there is something some action that is performed on a vector. So instead of doing it in 2D, let us now use our new find GeoGebra and try to perform it in 3D. I think that will make much more effect and understanding on us. Okay, so let me move to GeoGebra and then continue from there. So here we are. We have to just look at the left hand side and correlate it to the vector that we are going to see in this picture, right? So let's look at this vector, a general vector, simple vector I have taken, which is 1 2 3. Let me just rotate this to show you how this 1 2 3 looks like. You can please note down the orientation of how the x-axis is here, y on top and z coming out from the screen, and we are able to make out 1 2 3 very clearly now with that 3D effect. Okay. Now let's not worry about too many numbers here. Let me show you example by example, one by one. Okay. Let's take a very first example. Let's say that I have a matrix like this. We don't understand what this matrix does, right? So let's take our A vector and multiply it with this this matrix. So it's S times A, and obviously the answer is going to come as 2 4 6, right? So we can calculate this. So let us see what happens when we look at the diagram for this, right? So look at this. Right, so we see that there is the new vector is also in the same direction as the old one, which means keeping same numbers on the diagonal is probably only stretching the vector in the same direction, right? So you see that physical property of this matrix that is helping us understand this. It is only stretching the vector in the same direction. Okay. So that's one property that we are able to gain by looking at the geometry of it. Okay, fine. So let's move to the next example. So let's remove this S vector. Let's get back to the original A vector. Let me try and show you something else, right? Okay, I would like to show you now what is called as this M matrix, right? In the M matrix, you see I have got 1 0 0 0 1 0 0 0 minus 1. Okay. Now we really don't know what is this matrix doing. So let us see what happens when we multiply m times our vector 1 2 3. So obviously the answer is going to come out as 1 2 minus 3. Okay, so let's visualize and see what happens. Right, so there is a vector that has come out on the other side of this xy plane, and let's just rotate this diagram and see if there is something interesting that we are able to figure out. Right, so do you see something very interesting, right? So this is something like getting reflected on a mirror, is it not? Right, so you see in different angles. Maybe the best view would be to think like this, keeping the mirror perpendicular to us. It's very clear here that it's a mirror image of the vector. So what does this matrix do actually? The M matrix is helping us reflect a vector on the xy plane, right? So we thought it's a simple matrix, but it's actually doing enormous operation. There is a physical operation involved with that matrix. Okay, so let's move to the next example. Let me try and show you. Here I have a matrix called C. Okay, another matrix 0, -1, 0, 1, 0, 0, 1, 0, 1. Okay, not easy to understand what happens here, but let me try and show you what will happen if we use the C matrix and multiply our vector A. The answer is coming out to be -2, 1, 4. So let's visualize that. Let me remove this the reflection one, and let's look at this new one. Right, you see that there is a vector B coming here. So let me rotate this, and you're able to see something now. Right, so it's not very easy to understand what has actually happened to that vector. Right, so what I'm going to do is I'm just taking a general form of this matrix that we see. On the top we have this C matrix, right? Now instead of using the C matrix, you can look at this matrix, which is the D matrix, which is very general form of the C matrix, right? Now how did I come up with this, and how is this the general form of this, etc.? Right now we are not aware of it, but that's fine. What is interesting is to watch out for what happens when we are going to look at the D times A vector. So look at the D matrix. So remember that the D matrix is only a general form of the C matrix. In effect, we are looking at the same operation, right? We are looking at the same operation. We want to understand the effect more clearly. So look at this. This is D times A. So let us now visualize this. Let me remove the B vector off and turn on the F vector. Okay, so right now we are not able to visualize anything here. You can see that A and F are probably the same, right? There is it is drawn it on the same vector. Okay, that's because it is 1, 2, 3. There is no change. It's almost like identity at this point. Okay, because my t value is 0. Now let us try and change the t value, and as the t value changes, let us see how the vector is going to get animated. Right, so watch out for the F vector and see the animation. Right, we see something really interesting now. So I'm not sure if we figured out what's happening, but the idea is that we are seeing that the F vector is rotating, right? So in effect, what the C matrix is doing is rotating the vector, right? And it's rotating this vector right now. What's the axis of rotation? Around the Z axis. You can watch that this vector is simply rotating here. At one point it will even merge with A and then rotate to the other side. Because the t parameters are not very consistent here, we see that it stops at some point and comes, right? You can see here sometimes that it will merge. Yeah, you saw that it merged and then came on to the other side. Okay, so that's pretty interesting to see that this is rotating with the axis as the Z axis. So that's what that is what this matrix is intending to do. Okay, but we never figured out or never knew that all this was possible. Okay, so let me close the F vector. Let me remove the visualization and let me move to the next example. Right, so let me show you another example. We have a P matrix here. Look at this 1 0 0 0 1 0 0 0 0, and we want to see what this what effect does it provide. So let me take P times A, and that is 1 2 0, and let's plot this. Right, so now we see that vector. Let me rotate this and show you something very interesting. Right, so what in effect has happened, right? So try and see whether you are able to figure out. The interesting view is going to be when I keep it like this, right? So do we figure out something? It's quite clear that the 1 2 3 vector is coming out from the xy plane whereas the 1 2 vector or 1 2 0 vector is on the xy plane, right? Basically what has happened is that the 1 2 3 vector got projected onto the xy plane as 1 2 and 1 2 0, right? So it has got projected as 1 2 0. So that is why we are saying it is not coming out from the xy plane, right? So we saw 4 examples of matrices. Initially we started off by looking at stretching or scaling, and then we looked at reflection on the other side, and then we saw rotation, and now we are seeing projection, right? So pretty simple matrices, but they seem to do a lot, right? So with this background, let's go back to our math and continue with that. So if we look at the 2 by 2 matrices now, right? So can we get an idea of what they are attempting to do, right? We looked at that matrix in 3 by 3. So maybe this looks like stretching for me, right? So we can see the answers here. Okay, look at this matrix and look at the value here. I have 1 2 that has become minus 2 1, a probable kind of reflection that is possible here, right? So then the next one 0 1 and 1 0 maybe a rotation, right? So we are not very clear, but then we are trying to guess it out here, and this probably we're seeing something 0 0 here. Maybe this is a projection. Okay, but the interesting fact is going to be that we are going to derive all this. The stretching is definitely not it's not very difficult to understand, but at least for the other 3 we are actually going to do the math and try to figure out the matrices for such kind of transformations. Now that we are able to understand that a matrix is standing for some kind of a transformation, we want to first define what's a transformation in general and see how to associate it with a matrix. So we are going to define what is called as a linear transformation, right? So here is a definition of linear transformation. So I define it as a function on a vector x. The one and only property that the linear transformation has to abide by, the one and only property, is if I take a linear combination of vectors and apply the transformation, then it should remain linear combination of their individual transformations, right? And this is something that we are very well aware of, which is linear combinations that we are very well aware of. But when we say a transformation is linear in linear property it means that if you take a linear combination of the vectors, then it must result in the linear combinations of their transformations, of their individual transformations. Okay, so that's the idea of a linear transformation, and we very well know that a matrix follows this property, right? So if you take a matrix and try to multiply it with Cx plus dy, we know that because of using distributive property, we know that it becomes C times Ax plus D times Ay. So Ax and Ay being their individual transformations and C and D giving the linear combination, and therefore this property is true with respect to matrices, and therefore every matrix is a linear transformation. Okay, now we looked at several examples of linear transformations, and we may have a feel that linear transformations can do everything that we need, but that's not the case. So here are examples of what linear transformations cannot do, right? The simplest example is we cannot move the origin using a linear transformation, right? So attempt to do. So now that we understand that matrices are also associated, or we know that every matrix is a linear transformation, it means that you can attempt to do, right? Pick up any matrix and then put the origin and see where you can transform it. It is going to be impossible to transform the origin or move the origin. It's a great spiritual lesson as well. All of us have the same origin, and that origin does not change. That is very clear even in linear algebra. It's the same origin that's present in each one of us. It doesn't change. So apply that in the spiritual realm, and we do appreciate what Swami tells us, that it's the same indweller that is present in everybody. He is the same who doesn't change. Okay, so let me move to another transformation that is not possible. If we talk about the transformation on vectors that are basis vectors, then we can easily figure out the transformation on any vector x, right? Which means that you cannot, the transformation really cannot decide on a linear combination of other vectors. The more a transformation is defined on, once we are able to define the transformation on basis vectors, because of the single property, it's quite clear that the transformation can't do whatever it wants on the linear combination of vectors. So it is more controlled by the linearity there. So that is something that the transformation cannot do. It can't say that 1 1 I will transform to something and then 2 2 I will transform to something else. No, that's not possible, because 2 2 is a multiple of 1 1. So whatever transformation you get to 1 1, that can only be the double of it, right? So that's the idea that we are talking about here. Okay. Now we have a picture of what are linear transformations. We also understand that matrices do lead to linear transformations. We want to ask the other way, pose the question the other way and ask, do linear transformations lead us to a matrix? Does every linear transformation have an associated matrix with it? And if that is so, is it possible to figure it out, right? So that's the next part we want to look at. So look at this. It's the reverse one we are asking. Can every linear transformation be represented by a matrix? The answer is yes, we can. And the simplest idea is choose the transformation based on the basis vectors. So here is a simple example. Let's say I have a transformation we define from R2 to R3. This is my definition of the transformation, right? This is given to me. I take T of 1 0, it takes me to 2 3 4, it takes 0 1, it takes me to 4 6 8. Now you could ask, what does this represent? We really don't know. It could be rotation, reflection, or their combination, whatever. But can we find a matrix for it? That's the question, right? So let's see. So what we are going to do is, since we are able to figure out that the transformation is acting on the basis of R2, right? This is one basis of the R2, this is 1 0 and 0 1, the standard basis of R2. What we could do is simply pick up the vectors which are the transformed vectors of basis, put them in the matrix form, and we have the matrix with us. That simple it is to form the matrix A, right? So and we really want to attempt it on another vector, say minus 2 1, then all that we have to do is take the matrix A and say multiply it with minus 2 1, and in this case it happens to be 0 0 0, right? We can try this multiplication and check, right? So what have we got now? Every matrix is a linear transformation, and every linear transformation can be represented by a matrix. How do we do so? By choosing the transformation on the basis vectors, right? So we will take up different examples in this and try and figure out how to get the matrices for such transformations. So here is our first example. We would like to do rotation of a vector by 90 degrees in the counterclockwise direction. So with respect to what, so we are trying to measure angles in R2, right? So we are going to define transformation only from R2 to R2. We want to perform rotation. Now transformation is the physical action we are talking about. So we will have to perform rotation by 90 degrees in the counterclockwise direction. Okay. So let's think of this in R2. Let's pick up the 1 0 vector. It's lying on the x-axis and rotate it in the counterclockwise direction by 90 degrees. Where will we land? We're going to land up in 0 1. Similarly, take 0 1 and try to do a 90 degree rotation on 0 1. Where will we land? We will be landing in minus 1 0, which is in the other side of the x-axis. Okay. How do we form the matrix for a transformation? We pick up the transform matrices for the standard basis. So for 1 0 to 0 1, for 0 1 it's minus 1 0. I just picked up these columns and put them there. We got the matrix. Let's attempt to do and see if this is really right. If I take 2 3 as my x, try and multiply ax, which is like applying the transformation on 2 3, I am going to get a minus 3 2, right? So let us plot this and see if that is really true. This is the diagram, right? So we know this is my x vector, this is 2 3, and ax is the transform vector minus 3 2, right? So this is minus 3 2, and it says that this is the vector after rotation by 90 degree. Yes, it does look like this is a perpendicular, but if you really want to ensure that it is perpendicular, take the dot product of these two vectors and check, right? They are perpendicular, which means that our matrix A is working. Okay, doing it for 90 degrees is not it's not very difficult, but can we really do it for rotation by any angle, right? So that's the next question we want to attempt. So look at this. We want to try transformation of rotation by theta in the counterclockwise direction. Okay, so here is how we are going to do. Let's pick up the 1 0 vector on the x-axis. Let's rotate that vector by theta, by angle theta. Now by trigonometry we definitely know that the direction of that new vector is going to be, I can definitely represent it as cos theta sin theta, right? Okay, because the rotation angle is theta. Okay, now what's the magnitude of this vector? That is 1, and therefore magnitude of this vector will remain 1. So it is going to be 1 times, this is a unit vector, we know that, so 1 times this, which is nothing but cos theta sin theta. Therefore we got the transformation by just understanding the rotation physically. Okay, now let's attempt to do this on 0 1. So 0 1 is on the y-axis. Now try to rotate that 0 1 by an angle theta. So it will go and fall, let's say, into the second quadrant. Now the question is, what is the direction of that vector? So the first thing is magnitude. Magnitude is 1. So whatever I'm going to pick up here, I'm going to say 1 times that. That's fine. Now let's look at the direction of that vector. Okay, what is the way to represent that vector in terms of cos and sine is that we need the angle of that vector that it subtends with the positive x-axis. What is that going to be? With the positive x-axis, already we had the y-axis which is having a 90 degree, plus we have rotated it in the counterclockwise by theta. So overall the angle is going to be 90 plus theta. And therefore my vector direction, the transformed vector direction, is going to be cos of 90 plus theta and sine of 90 plus theta. And therefore this would become minus sine theta and cos theta. And that's it, we have got our matrix, right? So I just picked up these two columns here, cos theta sin theta minus sin theta cos theta, put them here, we got the matrix. Let's verify if what we have got is true, right? So let's assume that we want to rotate the 1 1 vector and we want to rotate it by 45 degrees, right? So think of that. Think of the 1 1 vector. Let's try and see here. Let's say that I have the 1 1 vector, which is at, we know that that is at the angle of 45 degree. We want to rotate it by 45 degrees in the counterclockwise, right? So we know what's going to happen. It's kind of going to merge here on the y-axis, which means that in effect it will be 90 degrees to x-axis. Let's see what happens, right? Try and multiply this. This is our matrix in general form. So I put cos 45 minus sin 45, etc. Fill this up. We have got this. I multiply this with 1 1. I'm getting a 0 root 2. Is that right? I know that its direction is definitely right because it's in the direction of y-axis. It's 0 here and there is something here, which means that this is in the direction of y-axis. We got this correct. Now we only have to check the magnitude. So then I can write this as root 2 times 0 1. Right? What's the magnitude of 1 1? That's root 2, and here I've got the magnitude to be root 2, and it's in the direction, the unit vector in the direction of the y-axis, which is perfect. That means that our matrix is right. Okay, so let's proceed to ask further questions on this, right? So suppose we want to find the inverse of the transformation T. Now that we have the matrix associated and like we are adepts and we know all kinds of techniques to find inverses, let's go ahead and find the inverse of A, and that will tell us the inverse of the transformation T. Okay, so here is our elimination strategy. Please do work out through all the steps and see if there are mistakes, and finally let's say that if these are correct, these steps are correct, here is my A inverse and I'm getting it as cos theta sin theta minus sin theta cos theta, whereas my original matrix was cos theta minus sin theta and sin theta cos theta. Okay, fine, that's great. So what have we achieved? We don't know at this point, but at least we can say that we figured out the inverse of the transformation by finding the inverse of the matrix A. Here is another question. If I want to apply the transformation multiple times, which means that first I want to rotate the vector x by theta 1, after that I want to rotate by theta 2. How do I do this? What we are going to say is, since we know that this transformation can be applied using matrix multiplication, I am going to say T of x using theta 1 is going to be A with theta 1 as a parameter times x. After that, multiply it with A of theta 2 in this order. But by associativity, I can even multiply these two and then apply it as one matrix on x. So here in my a theta 1, I have just put theta 1 as the parameter and theta 2 here for a theta 2. I multiplied these two in this order, and this is my answer. Okay. Now there is something interesting that's coming up. If we had to find the inverse of the transformation, we found the inverse of this matrix and struggled and got this matrix. If we had to apply the transformation twice, we multiplied matrices, struggled for it and got the answer. Now why don't we look at this in the physical sense? What if we look at rotation and ask what is the inverse of rotation in terms of the physical operation? My answer is going to be simple. Rotate it in the opposite direction by maybe say by the same angle by theta, and which is in the clockwise direction. That's it, right? And if we do that, that's the transformation which is the inverse of the original rotation transformation. So let's take a look at what they give us. So this is what we are discussing. Physically, what is the inverse of t and what is the meaning of applying multiple? One is rotating back by theta, which we said in clockwise direction. And what is applying multiple times? It is simple. First we rotate by theta 1, then by theta 2, which is in effect meaning that you have to rotate it by theta 1 plus theta 2. Okay. And what have we got? We said that any matrix for theta is going to be represented like this. And if you want to rotate this in a clockwise direction, it is nothing but a of minus theta. So let's substitute here minus theta in this matrix and see what we get. Cos of minus theta is cos theta, sin of minus theta is minus sin theta. So then look at this, we are going to get this matrix. And where did we just find this? It's the A inverse. So why did we have to really struggle to find the inverse? We could have just looked at the physical operation of it and come up with the inverse in no time. Now we see why we need to understand matrices and their relationship to transformation. Sometimes looking at it physically can give us the answer faster than actually doing Gaussian elimination with Gauss-Jordan. Let's try the next example. Look at the next example here. A of theta 1 plus theta 2 is this entire matrix, and we are saying that's got to be same as A of theta 2 A theta 1. How is that, right? So let's go here and see what we got. Right, look at this here, cos theta 2 cos theta 1 minus sin theta 2 sin theta 1. That's got to be cos of A plus B, or cos of theta 1 plus theta 2. Similarly, this is going to be sin of theta 1 plus theta 2, and similarly you can figure out the rest of them. And here it is. That's this matrix that we recently got, right? Again, just by looking at it physically, we are able to get the matrix in no time rather than computing it. Okay. So here are interesting questions. What if we inverse the order of rotation? What if I want to do first theta 2 and then theta 1? What do you think is the answer in terms of doing it physically? Would it be same as doing it the other way? Verify this, right? So try and verify this and prove that the matrix for it happens to be same as the one that you are thinking it through physical transformation. Okay, and similarly, what if I want to apply the same angle rotation multiple times, right? You could, I've just put it 2 times here. Maybe you can try and look at it multiple times and see really what happens. And again, physical versus the actual computing. Let's verify and see if we're getting what this is supposed to give, right? So let me move to the next example. So we move to what is called as projection now. With respect to projection, we are again going to define our transformation from R2 to R2, and the definition is going to be projection onto x-axis. Okay. So what would happen if I project the vector 1 0 on the x-axis? 1 0 is already on the x-axis. If I project it, nothing would change, which means that t of 1 0 will remain to be 1 0. Okay, what would happen to 0 1 if I try to project it onto x-axis? It will simply fall into the origin, which means that will become 0 0. That's it, we got our matrix 1 0 0 0. Okay, let's try and apply it to 2 3, right? So what will happen if you try and apply it to 2 3? I get a 2 0, which is right. Right, so take the vector 2 3, try and project it onto x-axis. You're obviously going to get 2 0, which means our matrix is right. Okay, again, just like as we did in rotation, let's try and see if we can do projection onto any line which is subtending an angle of theta with the positive x-axis. So remember this carefully. The simpler example was to project it onto x-axis, Similarly, you can even attempt to try something on projection onto y-axis. But what we really want to do is a general case. I want to project it onto any line that's subtending an angle of theta with respect to the positive x-axis. Now let's take a look at the geometry of it in R2 and try and see how do I figure out the transformation. So here is this diagram, and we will need a bit of trigonometry to understand this. This is my line onto which we want to project. Okay, what is the vector we want to project? The basis, the standard basis vectors. We want to project 1 0 and we want to project 0 1. So I take 1 0, I want to project it onto this line. Look at the way the perpendicular is, right? I shouldn't project it like this, they should not, it should not be perpendicular to the x-axis. When I say projection, it is with respect to this line, and therefore I project it using the perpendicular of this point to this line, my line of interest. Okay, and that meets at this point. Okay, I need to find the coordinates of this point. Okay, so before we do that, let's try and see. When I have this vector 1 0 and I project it here, this angle is 90. This angle is 90. This is given to be theta. I know that this distance, or this the shadow of this vector on this line has got to be cos theta. Okay, now that is a vector whose length is cos theta. I don't know what are the coordinates of it here, which will actually give me the vector components. How do I get that components? For that, I need to figure out what is the x and y for this hypotenuse, which is cos theta. So look at this triangle now. This is 90, this is theta. What would be my y and what would be my x? That's what we are interested in. So here is how I wrote. Cos of this angle is going to be adjacent x by cos theta. Sine of this angle is going to be y by cos theta. Now, how did I get this cos theta? Because that's my hypotenuse. So now how did I get that? That's what we recently explained. So this is a right angle triangle and this is my hypotenuse because this is 90. Since this is theta, this has got to be cos theta. How did I figure that out? Because this vector divided by this vector is going to be cos theta. This is just unit length here. So therefore this happens to be equal to cos theta. Right, so that's what we have got for this point. Similarly, use a perpendicular and try and project this onto this line, which is our 0 1 vector. Now I did not draw this here because it could tend to confuse us, so let me just I separated this triangle out here. So this is my vector 1 here you see this. Here is the perpendicular, this is coming and hitting this line, and this is our line, which means that from the origin to here this is the point where the shadow is falling. The first point is to look at how much is this length of the shadow. The length of the shadow here is going to be sin theta. Okay, let me explain how we got this. So look at the triangle here, right? So try and move this triangle somewhere here and you try and place this here. Look at this, this is theta. This angle will be 90 minus theta because this is 90, right? So this will be 90 minus theta. This is a perpendicular, which means that this is 90. This angle is here, this is 90. This is 90 minus theta. So this obviously has got to be theta. Now look at this triangle. This is the hypotenuse, which is 1. And since this is the right angle and this is theta, I know that this has got to be sin theta. Why? Because this is 1 unit. No, this is just a unit vector here. Okay, so the hypotenuse is sin theta, right? So remember that the length of the shadow here is sin theta. Suppose that's the point here. I want to figure out the coordinates or the components of this vector. Then I need to bring it down the x-axis and see where it hits the y-axis, isn't it? Right? So for that, again, we will push it down here and see how much is it covering in the x and how much is it rising from the x, that is the y in the y direction. Okay. Now looking at this triangle again, that would give me this is theta, this is my y and that's my x. Therefore, same principle you apply here. Cos theta is going to be x by the hypotenuse this time, which is going to be sin theta. And the other one is going to be sine of this angle is going to be this y, the height of this, divided by the hypotenuse, and the hypotenuse here is going to be sin theta. This is what we have got for the vector 0 1. Okay. With this in place, let's go and write down the transformation. T of 1 0 is going to take me to look at this, x and y, right? X is going to be cos square theta, y is going to be sin theta cos theta. That's what we put here. T of 0, 1 is going to be, x is going to be cos theta sin theta, that's here, and y is going to be sin square theta, and that's what we got here. That's it, we got our matrix. That's my projection matrix. And there are a few interesting properties with the projection matrix. Let's go through some properties. Okay, so here the first question, similar question like we had last time. What's the inverse of projection, or what's the inverse of this transformation? The idea is to bring back the vector from its projection. Try and answer, is that possible really? Right? So after you are projected, is it possible to get the vector back? Let me try and give you an example. If I take an example of projection, let's say that I have this vector and try to project it on the x-axis, right? This large vector, when I project it, would also fall here. I may have another vector here which will also fall here. I may have one more vector here which will also fall here. Now we are asking for the reverse, right? Given this point or the shadow, can you give the object back? That's absolutely impossible. And therefore, that's the answer we have got, right? So possible? No, that's not possible. But can we verify it from the matrix, right? That's the interesting part. Try and see this, right? So look at this matrix. I am trying to find, I'm trying to do an elimination to find the pivots, and you can see something very interesting that's coming up. It's saying no second pivot, which means the inverse doesn't exist. It's exactly same as the physical operation we just thought of, right? Now you see that beautiful relation that is coming between linear transformations and the matrices. Okay, the next question is, can we apply this multiple times and see what happens, right? So look at this. I want to first project project the vector onto some line with angle theta, and again project it onto the same line. That should ring something, right? That should give us an idea of what it's going to be. Okay, but in any case, I can do this with matrices, so which is nothing but a times a of x, which I can call now as a times x. Let me try and figure out what is a square. So I got it, right? So such a complicated expression we have got. But before we go ahead and try to simplify this, physically let's think of this and ask, what would this give if I project a vector onto, let's say, x-axis and project it again? It will remain the same. I don't think it is going to change, and that will happen for any other line which is subtending an angle of theta as well. Let's go and verify this. Is that really the case, right? So now let's try and simplify this, and you would be wonderstruck to see that it is same as our projection matrix, right? So interesting question. What will happen for a3 or a power n, right? The answer is pretty simple, but then try and work it out and then verify the answer. So we understand here that a square is equal to a for projection, which means that a itself, sorry, there is no inverse for this, so I was about to say it's the inverse, but then here a square happens to be a itself. Let me move to another example, which is reflection, and I guess this is going to be the last example for the linear transformations in this session. Again, we're going to define it from R2 to R2, and let's try and first work on reflection along x-axis. Let's think and see. Let us try and reflect the x-axis, that means 1, 0, it's lying on the x-axis, with respect to the mirror, which is also on the x-axis, because we said that we want reflection along x-axis. The answer is simple, it's got to be just 1, 0. Because when I reflect something, take a pen and put it on the mirror, that's the reflection as well, right? So the kind of reflection will just get hidden there by the pen itself, and therefore nothing happens for reflection along x-axis for 1, 0. Interesting question. What would happen to 0, 1? Right? If I try to reflect this, what would happen? It would go to the other side, and therefore I will be getting here a 0, minus 1. And that's the matrix that we picked up here, 1, 0, 0, minus 1. Let's try and apply it on 2, 3. We are getting 2, minus 3. You can imagine the diagram and see it is indeed the proper reflection along the x-axis. Now, as we did in the previous cases, we are moving ahead to a general case and asking, can we perform reflection along any line with an angle theta? Right? So again, we get into some bit of trigonometry here and a bit of vector algebra. Okay, Here is my line of interest, the blue line, that's subtending an angle of theta. That's the mirror direction, right? So this is how we have placed the mirror in that angle, which is subtending an angle of theta with respect to positive x-axis. We have to reflect the vector 1, 0 along this mirror, and we have to reflect the vector 0, 1 along this mirror. How do I do this? First, I take the vector and put a perpendicular like projection, just like projection with respect to the mirror. From the mirror perpendicular I draw and I get something. So this is the point where I meet. I take the same amount distance here and push it on the other side, and that point or that vector is my reflection of the 1, 0 vector. Watch this, right? This is my blue vector and the yellow vector. That's the reflection. This is the mirror, right? Based on this angle, you can clearly see it does look like a real reflection. Let's take the 0, 1 vector here. 0, 1 vector. What do? I first use something like projection, which means I drop a perpendicular from here with respect to the line of interest, right? With respect to line of interest, and for the same distance that I came, I go to the other side, and that's my reflection vector. Watch this. This is my blue vector whose reflection is this yellow vector. Now again, we have to get to finding out what is this point. Okay, so this is how we're going to figure this out. Now I have this angle is theta. Let's figure out what is this much, which is, we could use our projection idea as well here. Since we know that this is a right angle triangle, this is my theta, this is a unit vector, this has got to be sine theta. Why? Because sine of theta is going to give me this distance divided by a unit vector, which is just by 1. Therefore, this will be equal to sine theta. Same amount distance I have gone on to the other side, which means the magnitude of this vector, the magnitude of this entire large yellow line, which is perpendicular to the mirror, is 2 sine theta. Right, so that's what we need to figure out. So my magnitude of this is 2 sine theta, because sine theta plus sine theta. Okay, what is the direction of this yellow line? Right, what is the direction of this yellow line? What I'm going to do is I'm going to take this yellow line and place it here at the origin. I get the magnitude is 2 sine theta, but what is its direction? That's what we want to know. I would know that if we are able to figure out the angle that this angle, right? So I think I kept it in the wrong position. So if this is my vector starting here, let me take this and put it here. So I would get something like a parallel line here, right? So this is how it will look like, right? We have to figure out this angle between that yellow line and that it subtends to with respect to the x-axis. That's important for me to understand, because that will give me the direction of this line. Okay, so how do I figure this entire angle? Okay, look at this. This angle is theta. This triangle, this is 90. This is theta. If that is theta, here it is. This much is theta, and therefore this is already 90. Okay, let me repeat that. Sorry, I think that was not clear. So let me repeat this part. So look at this triangle, blue line, the sine theta yellow line, base blue line. This angle is theta. This is 90 degrees. This angle is 90 minus theta, because 90 and theta, so this has got to be 90 minus theta. If this is 90 minus theta, what will be this large angle, right? That's what we want to figure out. That's where we're interested. What will be this large angle? That will be 180 minus this angle. So calculate 180 minus 90 minus theta. That is 90 plus theta, right? And therefore, what would be this vector? This vector is going to be cos of 90 plus theta, this entire angle, and sine of 90 plus theta. Simple. And therefore, we want to figure out this entire vector in its direction and magnitude. And what is the magnitude of it? 2 sine theta. What is direction? Cos of 90 plus theta and sine of 90 plus theta. Okay. Now look at this. The reflection vector is here. This is the one in yellow. So in effect, what we have done is we have walked on 1, 0, and we have walked on this large yellow vector, and finally effectively reaching this vector, which means that I am going to do a vector addition. I walk on 1, 0, and then I walk on this. Therefore my reflection is a sum of these two vectors. Here it is, 1, 0 plus 2 sine theta times this entire thing. This is what I have got. Use a similar logic to arrive at this one, right? So let me try and explain this as well. Okay, so again let's look at this triangle here, the blue base, the hypotenuse, the perpendicular, this is 90, and let's look at what is theta here. This much is theta, this small angle will be 90 minus theta, this is 90, therefore this will be theta. If that is theta, this has got to be cos theta. In fact, this would be the adjacent divided by this hypotenuse, but the hypotenuse is unit length and therefore this length is same as cos theta. That's cos theta. We move the same amount on the other side of the mirror. In total, this entire length of this vector, the magnitude of this vector is 2 cos theta. Okay, the next idea is going to be how to figure out what is the angle that this line subtends with the positive x-axis. Okay, now what you could do is, either we could go and place it here, or since it started here and moved here, right? So we started here and moved down here. So I'm going to take it and then place it here at the origin. Similarly, the same thing we did here, right? We started here and we drew the vector here. So I should not be doing it in the opposite direction. Walk here and then walked here. So I picked up this and placed this at the origin. Then we got the direction. Similarly, I walk 0, 1 and then I walk this. So let's take this part and fix this at the origin. So take this part and fix it here at the origin. And that's what it subtends, right? So this line is going to look somewhat parallel like this. We need to figure out the angle now between this much, which is between x-axis and this new vector that we have drawn. Okay, how do we figure this out? How much did we get here, right? This was theta. The theta with respect to this positive y-axis. When I move this down here, this would still maintain. This would still be that theta. Therefore, how much will this be with respect to the positive x-axis? This has got to be 90 minus theta. Now look at this. We have got this vector which is going to be, its direction is going to be cos of 90 minus theta and sine of 90 minus theta. And we know the length of this vector. The length of the vector is 2 cos theta. And that's it. Let's do vector addition for getting a reflection vector, right? Look at this yellow reflection vector. So walk on 0, 1 and walk on 2 cos theta in the direction of this, and that's what we have got here. This is my expression for that. Take these two and we have figured out our transformation, and from there our matrix, right? So look at this. This is 1 minus 2 sine square theta and 0 plus 2 sine theta cos theta, that's here. Similarly, you can verify the other one on top, which is t of 0, 1. That gives me my matrix. Here it is, and that happens to become cos 2 theta sine 2 theta sine 2 theta minus cos 2 theta. So question again, what's the inverse of reflection? Before we venture out to actually find the inverse, let's try and ask, what does it physically mean to say what is the inverse of reflection? What are we saying? We are saying that if this is my vector and this is my reflection, what will be the reflection of this back with the same mirror? I will get back to my original matrix. Okay, I have 0, 1, I reflected this, got the yellow vector, I will reflect this again with the same mirror. Where do I go? I will come back to 0, 1 again. So what is the inverse of reflection? It's again reflection itself, which means this matrix must be same as its inverse. Is that really possible? Let's verify. Right, so let's do this elimination process and try to figure out the inverse. Please go through all the steps and check if there is a mistake, right? And if all this is right, look at what we have got. Look at what we have got here. Cos 2 theta sine 2 theta sine 2 theta minus cos 2 theta, exactly the same. We have figured out that the inverse of A is same as A itself. And that tells us something very interesting, that A times A will give me identity because A happens to be the same. And physically it's the same because we pick up a vector, take its reflection, again take its reflection, I come back, which is like nothing but identity operation on the same vector. Okay, great. Now we could also relate this to projection. So we could look at the projection matrix that we got earlier and try and see what you get here. 2 times projection minus I will lead you to this matrix. An interesting part is try and do a square here. Just like simple algebra, if you do this, we will find that 4p square and 4p will get cancelled because there is something that we figured out here. We said that p square is same as p. Right? Remember, there's a huge difference between reflection and projection. For projection, there is no inverse. Inverse doesn't exist. Here inverse does exist. Here the reflection matrix square is identity, whereas the projection matrix square is projection itself. So these two would get cancelled. I would still get I, which is what we got here, right? It's the same. That's it for this session. And what was interesting about this session is that we tried to relate physical actions or linear transformations to matrices, and we were also able to verify the actions that happen versus the matrix operations. Let us close this session with a prayer. Om Shanti Shanti Shanti.